Hi, I'm Ian Murdock. I'm from Richfield High School. I'm a senior and I do the science research class there. So my project's title is a wavelet-based method for generalizing molecular latent spaces for assisted traversal. Next slide. So this project is kind of the culmination of my appreciation of math and chemistry. So I am really interested in math, but I'm also really interested in chemistry. And when I was thinking of topics for my research project, I wanted something that could mesh with that. Um, However, that would require me to work on like more advanced math topics. So I contacted Dr. Zhaodi Wang at Western Connecticut State University. And over the summer, I worked on the project and I took classes there concurrently on like advanced math topics like advanced linear algebra and machine learning. And then he assisted me with the math concepts, but I also consulted Dr. Esmond Bieram, currently working at AstraZeneca, for advice on the like machine learning model that I use in my research. Next slide. Is yeah, okay. Sorry, it just froze for me. um, okay. So the main objective for this project is to look deeper at predictive chemistry. So to this end, I use a lot of different tests and on the different models that run on different wavelets to test the efficacy, and then kind of the byproducts of that are the wavelet-based model of the determining the viability of these models for molecular modeling, and then looking at the properties of the wavelets on the model's training. So next slide. So first off, just kind of an introduction to like why we would use wavelets for this kind of problem. So the problem that we're looking at here is a problem of generating a space, a latent space of all possible molecules from a set of molecules that we feed into this model. So I use SMILES, which is Simplified Molecular Input Line Entry System. On the top or middle right, that string of characters represents the picture on the bottom left. And in that way, this format allows you to use just a string of normal characters to represent not only the composition, but the structure of a molecule as it would pertain to IUPAC or something like that. And then you can also represent this as a series of characters or as a series of vectors. So in the bottom right, the method that I use is called one hot encoding, and yellow is a 1 and then purple is a 0. So each of these dots, the positioning columns represents a character. So you can turn one of these strings into a matrix, is what I'm doing. So next slide. So for wavelets, what's the wavelet transform? So the wavelet transform is well, specifically the discrete wavelet transform that I'm using is allows, when placed through on a data set, separates the data set into an A and a D part. We'll call it that. And A is the approximation, D is the detail section. So if you look at the bottom left, we have our starting matrix, and it's separated into these two parts. On the left, the greenish part is the detail, and the right is the approximation. You can see that the spacing vertically is the same, and it looks very similar to the original for both of them. However, the horizontal shift is a little off. But then when you place it through the inverse wavelet transform, which is also the transpose, which allows us to do some matrix algebra with that, when you put both parts into that transpose, it reconstructs the original data. However, this means, because it's a matrix, that you can also just only use the approximation section, which gives you a reconstructed approximate data piece, as shown in the bottom left, like the picture on the furthest right. which is the data that is a generalization of the original data, but it is a little fuzzier because it's generalized. Next slide. So wavelets, I use a few different kinds of wavelets. So for demonstration, I use the identity matrix, which is just a matrix full of zeros with a diagonal of ones. I put it through the wavelet transform, only take the approximation part, and then put it through the inverse wavelet transform, so you get that fuzzy generalized version. As you can see, the discrete Meyer and quafflets are both symmetric. So the pattern spreading out from side to side for each row is, well, symmetric, and the peaks are fairly distinct. However, if you look at Dobitsch's four-band, because it's asymmetric like this, the peak is spread out over two columns, and this could potentially lead to some issues with training in the future. Next slide. So my model is fairly simple. It really relies on the long short-term memory cell, which is a type of cell that really, well, a big issue in AI and in just like straight like linear models is that the inputs that you put in at the beginning are forgotten. The earlier cells, they're as the model trains with more and more cells, their effects like diminish. But LSTM uses this hidden state, the on the bottom left of that picture, which allows it to maintain information over a long period of time. So my model uses an LSTM to generate these cell state and the hidden state. It combines them, kind of squishes them down, reseparates them, and then puts them into a new LSTM. And what this does is it generates a new latent space of all the possible molecules by analyzing the data, rearranging the states of the first LSTM cell at the top, and then feeding the data in again to make a multidimensional like model of the molecules. Next slide. So for training, as you can see on the top left, this is the training over epochs. Epochs is just a cycle of the model. So it'll go through a certain amount of data and then stop and then go through the same amount of data again with the model having been trained up to that point. So as you can see, the data, unaltered data, actually has the highest loss at the end, and the asymmetric DB4 has the lowest loss. However, we'll see in a second that this isn't necessarily a only good thing. So using the model's weights, after the model's been trained, you save the weights, which are like the memory of the model, what the model has actually learned. And sampling character by character, you can take the probability of the model choosing a C for the first character or a N for the first character, and take it in negative log likelihood format. Negative log likelihood means that you take the logarithm of the probability. So if it's 1 over 1,000, the logarithm is -3, multiply it by -1, and you get this scale where lower numbers are much more common than higher numbers. As you can see with the normal in the bottom right, the first character is fairly confident. Considering all the possible outcomes, it's a pretty good guess. And then there's good separation between the second and the third, which also indicates that in some level it understands that there is a distinct separation between first and second characters. Although second and third can vary because of different possibilities, and that's a continuation through all the models. However, for DMA, the discrete Meyer and the quafflets follow the same pattern. However, the Dobitsch's four-band, as we can see in the first and second characters, are not differentiated, which could possibly be due to the asymmetry of the wavelet, which has the dual peaks that we showed earlier. And this could indicate that the model is poorly trained or that it doesn't understand the question, which would mean that it's learning, the loss is lower, so it's learning more, but it's not learning the right things. So if we went by that logic, the quafflets would actually have the best learning, best, because the loss is the highest and it's most similar to the original loss.
2 minutes.
2 minutes? Okay. So next slide. So these are just some of the molecules that I decided to use, or that are generated by feeding starting characters into the model that's trained. So I have these 4 different models, one with normal, quafflets, discrete mare, and double cheese. And as you can see, the smile strings are fairly similar for each of the entries in a row. However, the model is learning the connection between characters, and it's not learning the connection between structure and characters and structure. Um, so that could be a potential path for research in the future, would be using a nomenclature instead of smiles that allows us to look at the structure of the molecule and learn based on that. Okay, next slide. So the results of this experiment have really shown that the wavelet-based models can generate approximate latent spaces to that of an unaugmented one, although they are generalized, which is good because they have half the number of basis vectors. However, it really relies on the symmetry of the wavelet transform, because you want that single peak so that it's confident about which choice it's making and it's not wishy-washy about which one is the best one to take. And then eventually this could help simplify these complex latent spaces in these traversal applications. So like searching algorithms, drug discovery, different avenues that have you looking through these big data sets for molecules that are similar to one another. Next slide. And then for future research, I would apply the wavelet-based data to other types of encoder-decoder pairs. So that can include transformers, which use like floating encoder-decoder instead of just the, 1 row per character method that I used. I could also use other types of cells like transformers and gated recurrent units, which are kind of similar to long short-term memory. And then finally, I could work to discover the best model architecture for latent space generation, although that goes hand in hand with the second point.
And that's time.
Yep. And then the next slide is just thank you.